All right, so it seems like folks have just about finished rolling in. So I think we'll get started with the webinar. Again, to those who just joined, welcome. Feel free to say hi in the chat. Let us know where you're joining from. You're more than happy to hear from you. Just some quick housekeeping before we get started. This webinar is being recorded and will be made available. There will also be a Q&A at the end. So we do have a Q&A pane available. If you have any questions that come up during the webinar, please feel free to enter them there and we will answer them as they come in. So with that, let's get started. Before we jump into it, though, I do want to ask a quick question. On average, how long do you think it takes engineers to fix problems with Kubernetes deployments? We actually have a survey that we're going to pull up with a few different answers. Feel free to choose any answer that you think is the correct one. We won't make fun of you if it's incorrect. Don't worry about it. You're not being graded on this. But yeah, definitely feel free to select one of those answers and put in your vote. And this covers basically from when a problem is first detected to when it's been resolved. All right. Got your answers in? Good. So the answer, drum roll, is on average about 8 days. So this amount of time varies, of course, depending on what type of reliability risk is found in your cluster, but it generally falls between 6.5 and 11 days. If you're wondering where these numbers came from, these are based off of our own internal research into how folks find Kubernetes risks using our product, and we'll show that a bit more later. 3%, wow. You guys are optimistic. I respect that. Surprisingly enough, it does take a while for folks to discover issues. If your team has been finding them and fixing them in a shorter amount of time, awesome, way to go. But in general, it does take teams a bit of time to find these risks. And part of our job at Gremlin is trying to make that a bit easier and reduce that time a bit. So who are we exactly? My name is Andre Newman. I'm a senior reliability specialist at Gremlin. I spend most of my time writing about chaos engineering and reliability testing and enabling customers to successfully adopt Gremlin. I get my hands in the Kubernetes clusters a lot, so this is a topic that I really like talking about. And I'm joined by Dan Muret, who I'll let introduce himself.
Hey everyone, this is Dan Muret. I'm a senior solutions architect, so I work with customers to help with their chaos engineering, reliability management practices, sure everything's working well, and helping design and implement testing practices.
Cool. Thanks, Dan. So a quick look at what we'll be talking about today. First, we'll be explaining what exactly is a reliability risk. What does it mean? We'll talk a bit about how do you determine what's a risk and how do you prioritize fixing risks. We'll go over 10 of the most common risks that you find in Kubernetes clusters. As I mentioned, Dan will run us through a demo about how Gremlin helps with identifying these risks. And then we will end up with Q&A. So jumping into it, what is a reliability risk? Generally, we can define it as any sort of latent issue in your environment that has the potential to impact customers. These can include things like node failures, a pod or container crashing, missing auto-scaling rules, things like missing load balancer or application gateway rules, and everyone's favorite pod crash loops. And the reason we highlight reliability risks is that by finding these risks early on, we're able to prevent them from becoming larger issues like incidents or even outages in production. It's kind of like the saying goes, an ounce of prevention is worth a pound of cure. The more of these risks that you can find and fix early on, the less chance you'll have of them becoming something much bigger down the road. And when we think about all the different risks that are available in Kubernetes, Kubernetes is a really complex system with a lot of moving pieces. How do you determine which ones to focus on? So we'll start with one of the most important, we'll start with one of the most important features in a Kubernetes stack. So if you think about what we really need from a Kubernetes cluster, one of the big ones is scalability, right? Can the system quickly respond to changes in demand? Can it scale up and scale back down? And do we support scaling of our pods and clusters? Another big aspect is redundancy. Can our applications keep running even if part of our cluster fails? Do we have replication across multiple availability zones or even multiple regions that if we lose a data center or an AZ or a rack, it doesn't impact their services? Next is recoverability. Can Kubernetes recover if something fails? Can our pods and nodes auto restart after an outage? And how long does it take for Kubernetes to detect and restart crashed pods or failed nodes once it does? And then there's consistency or integrity. Are your pod replicas all using the same container image? Do you have any obsolete code running anywhere? Do you have any failed rollouts or deployments that have stopped halfway, where you might have different versions of the same container image running at the same time? So if we take each of these four criteria and kind of dig into them a bit more, this helps us break it down into the 10 most common reliability risks that we see. And these are organized into categories more for convenience. A lot of these are kind of standalone, but they give you a good sense of what the different types of issues you can run into are. So starting from the far left, we have, of course, resource risks. These are things like we're missing CPU requests in our pods, we're missing memory requests, we haven't set memory limits. We're not sure how our pod will allocate resources and how our cluster will be able to handle provisioning for those pods. Next, we have redundancy risks. These cover, AZ redundancy, but they also cover things like liveness probes and availability probes. And probes are super important. I'll dive into this a bit more later for redundancy, but also for keeping your pods up and running. Next are container risks. These include the really fun error messages like crash loop backoffs, image pull backoffs, what happens when your initialization container throws an error, and what happens if you can't schedule your pods. And then we'll talk a bit about more application-specific risks. And this is the application version non-uniformity, which is having multiple different versions of your application running at the same time. So if we jump right into it, we'll start by covering resource and redundancy risks. At a high level, this is about ensuring your pods are replicated and have access to the system resources they need without your cluster becoming unavailable or not having resources or being able to scale. So this includes things like CPU requests, right? In Kubernetes, when you're deploying a pod or container, you're able to specify how much CPU resources should be allocated to that pod or container when it's starting up. If your pod doesn't have enough CPU allocated to it, it could run more slowly, it might lock up. Basically, you want to make sure that there's enough performance available to give that pod the power it needs. On a similar note, you want to be able to set memory requests as well. And this is the minimum amount of RAM that your pod needs. The thing about RAM especially is that if your pod runs out of RAM or it doesn't have enough, or the node doesn't have enough RAM available, it won't just slow down, right? It could lock up, you could have system crashes, or you could have your system start terminating resource intensive pods in order to make room. You might know this as an out of memory or OOM killer. If you think about something like a large language model, right? LLMs take up a lot of RAM. If you just deploy a pod that runs an LLM and you haven't specified how much memory to allocate to it, it could very easily not have enough and not be able to schedule itself onto a node. So that's where that becomes very useful. And kind of on the flip side of that, we have limits. These set an upper cap on how much resource a pod can use. So let's say that same pod has a memory leak. If we let it run long enough, it will keep using memory until it basically exhausts the amount that's on your node. This will lock out other pods on that same node from being able to run on that same host. But if we set a limit, Kubernetes can detect when the pod exceeds that limit and stop it or restart it before it goes too far. So for greatest reliability, that's why we recommend using both requests and limits. And of course, fine-tuning CPU and RAM doesn't really make any difference if your node or your pod fails. That's why redundancy is so important. First is simply making sure that you have a way to monitor for failures. Liveness probes are a very easy way to do this, since they basically just periodically check that the pod is still running and able to respond to requests. And similarly, if your pod isn't running or doesn't respond properly, you can have the probe restart the pod to get it back up and running successfully. And now, stepping up a level to the node level, while it is important to have pods replicated across 2 or more nodes, it's also really important to have replicas across 2 or more availability zones, or AZs. AZs isolate your services so that even if an entire data center or rack fails, you still have a fully separate environment to shift to. Likewise, you want to make sure your pods are replicated across AZ so you can reliably fail over. As you can imagine, we hear quite a lot of stories about these outages as they happen. Um, if you've ever used AWS, you might have some horror stories about US East 1. Don't get me wrong, AWS is incredibly reliable given their scale, but they do have some pretty big failures sometimes. So if you're a cloud customer, there's not much you can do about a zone or region failing. But if we have a cluster that spans US East 1 and another region like US East 2, you have a much better chance of maintaining service if one of those regions fails. And I'm sure, Dan, being on the front line of this work, you probably had some resource and redundancy risks that you ran into.
Yeah, a couple of thoughts here, right? I mean, memory and CPU requests and limits are great, not only for managing your application, making sure they have enough of those resources, but for also, right sizing your clusters and making sure you're not paying for a lot more than you need. The other thought I had is on AZ redundancy. Of course, that's more of a cloud-focused term, but the way Gremlin reads this can also be configured to work even on-prem clusters. So definitely something to reach out to us if you have any questions. Happy to help you set that up.
Cool. So now we'll look at risks that aren't necessarily affected by your cluster or node configuration directly, but by the containers themselves. And these are our application and container risks. So first of all, Kubernetes makes it unfortunately easy to run multiple different versions of the same container. Like, I'm sure we've all heard of the latest tag, where if you put on a container image and use latest, it just pulls whatever the most recent version of that image is. The great thing about that is that it always keeps your container up to date. The downside of it is, imagine if you're doing a deployment while that container image is being updated. If your node pulls down a newer version of the image compared to the ones that are already running, you could have two wildly different versions of the same container running on your cluster without even realizing it. And the solution to this is using a fixed identifier like a digest or SHA-256 or even a label that you know doesn't change. You want to be able to specifically pinpoint a specific version of your container image while you're deploying it. And this way, even if you use like a rolling update to gradually upgrade instances over time, or replicas rather, you can feel confident that you don't have mismatched versions running at the same time. The next one, everyone's favorite error message is crap shoes back off. Anyone who's worked on Kubernetes at any point, from a beginner to somebody who's a bit more senior, has probably seen this message. All this says is that you have a container that, for whatever reason, crashes on startup. And typically Kubernetes will retry a few times before it marks a container as crash loop back off status. So at least you have a few chances to check to make sure that it does run successfully. The chances are, while this may be a problem with the deployment itself, it's also likely that something's happening within the container related to the application that's failing. So the way to approach this is check your deployment logs, check your container logs, and that should help you narrow down the causes. So similar error message is an image pullback off. This happens when the node can't retrieve a container image. Maybe the image name has a typo in it, or it references a container registry that's private, or your node's behind a firewall that only allows certain kinds of external traffic. In any case, fixing this is usually as easy as just making sure that the container name and URL are spelled correctly, and that you have permission to access the registry and then retrying the deployment. We also have init containers. These are containers that run before your primary container starts. So that's an example. Imagine you have a database container, but you need to download the database beforehand. You could use an init container to retrieve these files so that the database container can just access them directly as it's starting up. But as you can imagine, if that init container failed or crashes or couldn't complete, this could prevent your app from working entirely. So it's really important to be able to watch for these types of errors especially. And lastly, which probably seems the most obvious, is keeping an eye out for pods that can't be scheduled. This usually means that your cluster is too small or too tightly packed and just doesn't have the available resources, or the pod requires a resource that just isn't available, like a persistent volume, or like, let's say, a GPU for a machine learning model. So Dan, any additional thoughts on these? or other
Yeah, yeah.
experiences with them?
Most of these, the back offs and stuff are usually easier to spot, right? I mean, if you're checking the status of your pods, those tend to stand out. I think out of this list, the application version uniformity is the most likely to go unnoticed. So I think this is a good check. Most of the time, what I see is customers running latest for the image. And like you said, especially if you have an environment that's you're doing rapid development or uh, your pods are scaling up, and so they may grab different versions, and you could see some inconsistent behavior. So that's a good one to keep an eye on, and the detected risk makes that easy to spot.
Cool. So we've covered some of the more common risks. I also want to take a chance to cover some possible mitigations or approaches that are being used today. One that you might be familiar with are admission controllers. This is a feature that's built directly into Kubernetes. Basically, what they do is they're automated processes that check and validate objects that are being deployed. Typically, these are used as gatekeepers to ensure like the pods meet a minimum level of security, but they can also be used to check for reliability risks. And while they are a great idea, they do have some shortcomings. One of them being that they're only cluster or namespace wide. When you define an admission controller and you apply it, it only covers a very small part of your Kubernetes, your entire Kubernetes deployment. You can imagine if you have multiple clusters or multiple namespaces that different teams are working through. How do you make sure your admission controller applies to all of them? Who knows? Next is that an admission controller only really evaluates risks when a deployment is created. What if you have something like an in production change or you have configuration drift where your pods don't necessarily meet the same specification that they had when you first deployed them? Admission controllers can't really go back and recheck an already deployed resource to make sure that it's adhering to the same policies. And then what if you have a deployment that breaks policy, but you want to deploy it anyway? Admission controllers are honestly very strict. They're either a yes or no. They'll allow something through or they'll block it if it doesn't meet that policy. So let's say if you have something that you need to deploy that's like a fix or that you'll come back to later, these will block it from going out. So generally, ACs are useful, but what we really want to have is a way of identifying these risks that are multi-cloud, evaluates continuously, and preferably is non-blocking. And another thing that's common, of course, is observability, right? If you're already monitoring your systems, do you really need to do more? As you can imagine, observability is good, but it also has some shortcomings in this regard. The main one being that observability is reactive. You don't really know something's happened until after it's happened, and your observability tool has had a chance to digest it, process it, analyze it, and then finally alert you on it. Observability tools also miss a lot of risks that are present before deployment or even during deployment when a lot of these risks can be detected. Unless you have observability set up in like a pre-production environment where you do all of your testing, chances are you won't be able to find these risks until, again, after it's already out there and your tool has gone over and identified it. And then, of course, observability requires additional setup, tweaking, validating, all that fun stuff that goes into making sure that it's actually checking the things that you want it to check and sending alerts when you need it to. So there's a whole lot of processes that go in before you get this even up and running in the first place. So again, we need a way to be able to find these risks quickly, to be able to surface them in a single location and track them so that we know not just when they appear, but when they're resolved. So we've looked at the risks and the current methods and how they're falling short. So let's look at what it will actually take to implement a system that finds these risks, finds them at scale, like in an enterprise organization, and is easy to use. So taking what we know to monitor and surface risks like these, we need our approach to be automatic, right? We want it to be able to run continuously, not just during deployment or provisioning or in our testing environment. It should be available all the time and able to check and see when our pods change, not just when they go out. We also need something that's comprehensive. Right? It needs to be able to analyze all of our deployments across all of our namespaces, it needs to be able to provide the same insights into whatever service we throw out on the cluster, whether it's at risk or whether it's not at risk. Ideally, this would be universal too, right? Able to work across all Kubernetes clusters, across all Kubernetes environments. Doesn't matter if it's self-hosted in a data center that you own or fully managed in the cloud. The system should be able to work across all clusters and give universal insights that are universal across all those different clusters as well. And we want this to be able to be fast, right? We want to be able to detect and report on these risks as close to instantaneously as possible. The shorter we can make that gap, the less risk we have of having an outage or a major incident that impacts our systems and our customers. And that's really the ultimate goal of all of these, right? Is to be able to build systems that our customers don't notice if they go down, or that are easy to come back up if they do fail. So at Gremlin, we've looked at these problems and the shortcomings of the solutions that are already out there. And in response, we created a feature called Detected Risks. Our goal is to find and surface these lurking reliability issues as quickly as possible and present them so you can fix them before they ever reach your customers or your production systems. We built this right into Gremlin, so you can easily monitor all your Kubernetes services, whether they're running on-prem, in the cloud, hybrid cloud, or whatever other unique configuration you might have. And in a few minutes, Dan will show what this looks like in practice, but I'd like to set a bit of context first before we jump into the demo. So in the demo, we're going to be looking at a Kubernetes application called the Bank of Anthos. This is basically a sample application that replicates a banking website and a full-on banking service. There are about a dozen services in the app, but the one we'll be looking at is called the balance reader, which you can see right here in the middle here. Sorry, in the middle right, that's what I meant to say. The situation is the balance reader service is responsible for showing users their account balance. And as you can imagine, this is a pretty critical service, so we need to make sure that it's reliable. We'll use Gremlin to find its risks and actually resolve one of them so you can see how this works in practice and firsthand. And so with that, I will show it or hand it over to Dan to show how detected risk works.
Andre, we'll jump into it here. So this is, of course, the Gremlin interface. We're looking at our services tab here. So like the architecture diagram that Andre pulled up, I've got 3 different components of the banking application shown here. So I've got my front end, I've got ledger writer and balance reader. Over here on the right, we can see the detected risk and how many I have for each of these services. So we look at balance reader, right? And I go in and look at my detected risk for this balance reader. We can see I've got 4 out of the 10 detected risk that are showing at risk now. So if I click on any of these, scroll down a little bit, you can see that we give you a little bit of information here, what it is, why it's a risk, how to fix it, implementation details, that sort of thing. So depending on what, which risk you select here, of course, this changes, tells you the information that you need and kind of how to go about looking at this. So the nice thing about this is these are all passive validations. We're just reading your configuration and surfacing these up. So it's relatively easy to fix these, right? So I'm going to kick off a script here on the back side that's going to fix this. But what I've done is I've basically exported my configuration for this deployment. And I thought I'd just kind of show a quick side-by-side to see what we're doing. So to address the zone outage or the zone redundancy, you can see I've scaled up from number of replicas from 1 to 3. Basically using the scheduling policy on EKS, I'm able to just increase my replicas. It'll spread across my hosts that are in different AZs. I've also added a liveness probe to my definition. So I've added a liveness probe, all the settings and stuff for that. And then I've also added CPU and memory limits and a CPU request to my configuration as well. So I've applied these. Of course, you can do this multiple ways. I just delete the deployment and redo it since this is kind of a test environment. You can, during normal rollouts, you might have to make other changes, that sort of thing. So let's take a quick peek here. I'm going to go back here. Let's do a refresh and see if Yeah, so we've mitigated, at least two or three of these. This one sometimes takes a little bit longer to refresh. You can see that we've now mitigated. I've got my memory limits, my CPU requests all set now. Those are all mitigated. So again, we can refresh this. This pulls in again every 10, 15 seconds, depending on how long it takes for my deployment to run. So this is great. Now, kind of keep in mind, these are all potential risk. So these are all things that, may cause an issue, not saying that they are going to cause an issue, right? So these are things that just to be aware of. The other thing that you'll notice is for those of you that are familiar with Gremlin, is that we have added the ability now to add the detected risk into your reliability score. So similar to when you run a typical CPU memory test, a zone failure test, those sorts of tests, based on the detected risk that we see, and we can see that AZ risk is now cleared up as well. That we get a portion of our score added to based on detected risk. So if I don't have any detected risk, I get, of course, the full percentage towards my score. So now that I've created the service, I've made the updates, I've made the improvements to it. I've also now mitigated those risks, and so I'm back to a good score, and I'm ready to continue on.
Awesome. Thanks, Dan. I'll put my screen up again in 1 sec.
Yeah, and one thing we can touch on maybe real quick as well. We also have a report, right, that shows detected risk over time. So this gives you a good way to keep track of this trends, see how your reliability posture is improved over time in terms of risk. So you can see, when I built this cluster, I had 9 or 10 risk, and as I've made changes, done some testing, prepped for different things, you can see those risks kind of continue to go up and down. Now that I've got everything up and going, I've got zero risk showing. And then this shows basically across the environment, the different risks. So if any of these are at risk, this lets me see kind of at a higher level any risks that I might have as well. So just a quick little handy report that, of course, you can export, pull out, that sort of thing to look at as well. Andre, back to you.
Awesome. Thank you. All right. So Dan showed us a whole bunch about Gremlin, but I would also like to talk a little bit more about it. If you've been following us for a while, you probably know we got our start in chaos engineering. That's still a core part of our product, and we're continually improving our fault injection tools just to make them easier and safer to use. On top of that, we've also started building standardized reliability testing into Gremlin, and Dan showed that with the reliability score and the different categories that contribute to that score. This lets you create test suites consisting of chaos engineering experiments, which you can then assign to different teams in your organization. This creates a single standardized measure of reliability that all teams follow. We also use the results to generate that reliability score that you saw, which is really a measure of how well each of your services meets those standards. As Dan showed, we roll this up into a dashboard, but you can also drill down into the individual tests to see where and when a service failed. If you're interested in running larger scale tests, we also let you build, manage, and run game days directly from our web application. And of course, we're built from the ground up for enterprise environments and for running these sort of tests at scale. We take security and safety very seriously. It's a core part of our product that's been built into from the start. So you can totally run these tests in production on your servers and make sure that they're reliable and resilient. And of course, you can always learn more about Gremlin by going to our website at gremlin.com or following up with us after the webinar. So that concludes the presentation portion. Now we're going to open it up to Q&A. As a reminder, there is a Q&A panel that you can enter your questions into. Feel free to do so, and we will address them as they come in. So we did have one question that I would actually like to See if I can do this correctly. So the question came in that asks, occasionally AWS or AKS containers become unresponsive after a time and enter an unstable state. Upon restarting the container, resumes normal operations. What might be causing this issue? I have a thought, but Dan, I opened up to you first to see if you have insights into that.
Yeah, I mean, that could be several different things, right? I mean, it could be, the type of instance you're using. Are you using spot instances, for example, that, spin up and down on demand? Sometimes that can cause, delays in those type of things happening. Um, I think that's a good use case for liveness probes, right? To make sure, that they're up and responding and functioning. If not, let the system handle restarting this.
It's actually a much better answer than I had in mind. So thank you for that. Appreciate that. Yeah, it's just it comes down to it could be any number of issues. Live disposal would be great for keeping it up and running. If you want to troubleshoot it some more, I'd recommend looking into logs, container output, maybe querying it with the Kubernetes command line or a dashboard just to see what might be causing the underlying issue. But in the meantime, definitely use probes to keep that up and running.
Yeah, I've got another question from Tanae. Kind of a follow-on from an earlier question about increase in memory usage on a JVM heap. So Gremlin by default, and this is maybe a little bit off topic, but good question nonetheless. Um, so we don't increase the memory in the JVM heap with the native Gremlin tool. So by default, the memory test that we do is going to increase system memory and cause memory pressure. Kind of think of it as a noisy neighbor type of an experiment. We do have a product though called failure flags that would allow you to increase memory or cause other failures at that JVM level. So happy to talk about that, but that's probably too far off topic for today.
Right, awesome. So another question that came in on where can we find our clustered node details in Gremlin and how can we understand about the health checks? So when you log into the Gremlin web application, and I don't know if Dan, this is something you'd be able to share on your screen since you had Gremlin open. If not, don't sweat it too much. But within the Gremlin web application, we allow you to see all of the agents that are connected to your Gremlin account, and this includes Kubernetes clusters. So you can go into a web app and see which clusters you have connected, what namespaces are available in them. And then when you go to run a test on that cluster, you're able to select which namespace, which deployment or pod or service you want to target. And as far as health checks go, when you log into the Gremlin web application, we have a section that's specifically for health checks. You'd find it in the navigation pane on the left-hand side. That'll show you all the health checks you have available and also give you more information on how to create and add additional health checks.
And I've got mine up, but I think you may still be sharing, Andres.
Oh, sorry. My mistake.
All good. So yeah, so here's the agents tab, right? So if you look at the agents tab here on the left, you'll see the different active agents with all the tags that we pulled in as well. So this is kind of what the agent looks like. Kind of to answer the other question, I think it's from somebody that's anonymous. What form does the Gremlin tool take or the agent? In Kubernetes, it's a daemon set, so it's typically deployed via Helm chart, and then we basically run a daemon or a pod on each node, so we have that visibility to run the experiments.
Cool. Next question is, where can you find the different chaos faults available with Gremlin? And also, is there an option of writing custom faults based off of your individual requirements? So as Dan's showing, when you go in to start a new experiment and you select the resource that you want to target for that experiment, we show you all of the different options available here. We use 3 categories primarily, resource, state, and network. In each of those categories, you have access to all of the different faults in our library. The one exception is changing the system clock, and that's just a limitation of Kubernetes itself. you are still able to run that on just a regular host or node. But because containers don't really have access to that, we mark it as unavailable. But everything else, resource, network, shutting down or restarting, those are all available through here too.
Yeah,
And
it's
if
also
you do
available
want,
on the documentation site as well. So just gremlin.com/docs. On the left-hand navigation tab, there's a section for fault injection that has the different experiment types and more information about what they are, how to configure them, all that good stuff.
yep, definitely. And as far as writing custom faults, we don't have that available through this interface, but we do, like Dan mentioned, we do have failure flags, and it does give you the option of implementing custom behaviors based off of essentially you define in your code what you want to have happen while an experiment is running, and you can sort of toggle them on and off that way. Oh, Dan, I think this might be a good one for you. How would network attacks work in case of pods running on different nodes?
Yeah, it works just fine. Like I said, the agent's deployed as a daemon set, so we have a Gremlin agent on each node. So depending on where those are running, we can impact the network on multiple nodes, different containers, all at the same time. So you can do that, for basically an unlimited number of pods at a time. So it's fairly simple to configure. You just select your deployment inside of Gremlin and then the network, and then we take care of all that on the back end.
Perfect. And another good question that came in, what's the difference between scenarios and experiments? You can think of scenarios as experiment workflows, right? An experiment basically allows you to perform one specific type of fault injection. So you can create an experiment that does, let's say, use up 50% of the available CPU or of the CPU that's available to this pod. Whereas with a scenario, you could take that and build on top of it. So let's say you have an experiment that uses 50%, then in the next step you use 75%, and in the next step you use 90% to create sort of a cascading fault, basically. So essentially scenarios that you take experiments and create more complex, more involved workflows out of them to simulate larger scale or more complicated types of faults. And on that note, we do have a library of recommended scenarios that are included just in Gremlin by default to give you sort of a head start into seeing how to build your own scenarios and how to use them.
All right. Let's see. Next question. One of my favorite ones is using Gremlin in production. Any specific set of instructions and any scenarios we're testing in prod using Gremlin went wrong and what was the resolution? Yeah, so that's typically a maturity type of activity. I'm not aware of anyone that started testing in production. Typically, the testing starts in a test or sandbox environment and then moves closer to production. But we definitely have multiple customers that test in production. A lot of times, those are done during change windows. So, if anything does go wrong, but with the recent developments in Gremlin in terms of tying into your health checks, things like that, it really helps mitigate the chance of anything really going wrong when you're running the test. So the health checks monitor your application for you. If you exceed any of your thresholds, will stop the test automatically to kind of prevent those type of scenarios from happening.
Cool. I did see a question come into the chat window that asks any performance impact due to installing Gremlin agents on pods. The short answer to that is there's a very minimal set of resources that the Gremlin agent uses. Typically, it's barely even detectable. It even includes network traffic, but it doesn't have a performance impact on your pods themselves. The way Gremlin works when it actually orchestrates an experiment is it'll create a sidecar container that runs within the same pod but separate to your main container, and that's how the fault is injected. So your original containers don't get modified at all. They're still the exact same. we just build that sidecar to actually inject the fault once you actually run that experiment, and then the sidecar gets pulled away once it's done.
Yeah, just to clarify, the agent typically doesn't install at a pod. It's installed as its own separate pod that runs one per host. So you're only running one agent per host. So it's very very low overhead. When it's idle, all it's doing is pulling our control plane to see if there's any attacks to run. So it's a very low overhead agent. It's nothing like some of the other agents that are available.
Then the other question that came through is, do we have faults to inject latency or errors into downstream apps to validate if there is any cascading impact on the calling app? This is actually a perfect use case for, we have a couple of experiments that can work with that. The main one being latency. We also have a packet loss experiment. And what you can do with that is, if you know what your downstream application is, you can run latency or packet loss on that one, and then monitor your calling application to see how it behaves or how it responds in response to that. And a good automated way of doing it with Gremlin is creating a health check that checks your calling application. Maybe it checks for response time or a specific error, and just be able to monitor that automatically while you're running this experiment on your downstream app. That'd be the way to do that. All right, I'm not seeing any other questions come through. If you do think of a question afterwards that we didn't get to, we'll have a survey at the end of this webinar that you can fill out. You can also come over to our website at gremlin.com/contact, and we'll be able to answer it for you there as well. But in the meantime, I'd just like to thank you so much for joining us here today. Definitely hope this webinar was helpful for you all and informative and useful. Again, we're going to have a short survey after the end of this webinar where you can let us know how we did. That really helps us with being able to make these webinars, to be able to improve them and put them on regularly to be able to help out teams like yours. And if you want to be able to get started with trying out detected risk for yourself, or even just to learn more about it and how Gremlin works, we do offer a free trial. Just head over to gremlin.com/trial to sign up for that. And yeah, start getting a report of your detected risk in just a few minutes. So again, thanks so much everyone for joining us. Really appreciate your time. And yeah, hope this was helpful for you.